Greetings. In this lecture, we're going to finalize a series of segments on the mechanical behavior of materials by taking worked examples to illustrate a few interesting points. So we have discussed that we have a few formulas that we could use. And the formula, for example, for the logarithmic strain is the natural log of L over L0. The formula for the engineering strain is delta L over L. We also know that A0 L0 is roughly equal to A times L. We also know that sigma 0 is P over A0. And we know that sigma, which is the true stress, is equal to P over A. And when we have deformation in the elastic range, then the stress is equal to one constant times the strain. This constant, the single constant, is Young's modulus. And when we transition to plastic deformation and we use the true stress and the true strain, then the equivalent to this Hooke's law is another correlation between stress and the strain, and this correlation we can write it as sigma, and the prime is indicating true. Sometimes we do not differentiate, depends if we have small deformation. If it is large deformation, then we can differentiate. So let's say that true stress is equal to a parameter sigma 0 times the true strain to a power m. And this parameter is called strength coefficient. And this parameter here is called the strain hardening exponent. So this is kind of a quick summary. Let's take an example 2.1 to illustrate how we use that. So we have IC steel 1018, and it has a yield stress of 32 KSI, ultimate stress of or strength 49.5 KSI, fracture stress 91.1, and then the two parameters that describe plastic deformation in this Ramberg-Osgood formula is sigma 0 is 90 and the strain hardening exponent is 0.25, and the fracture strain is 1.05, means 105%. So we want to find the new values of the strength of the material, given that we have 15% reduction in area. So the reduction in area, we have to write a formula here that A0 is larger than A, and is larger than A by 1 over 1 minus W. So this formula here is important because we can also use it with the volume conservation formula to convert it to lengths if needed. For here, we're given a reduction in area of 15%. So once we have a reduction in area 15%, we can calculate the new area, and then that can give us an ability to determine the length from the volume conservation and hence the strain. So in this case, A0 over AI is 1 over 1 minus W, and plugging in 15% for W, then we get A0 is larger than AI, is 1.1676 of AI. So this is the first example that we have here. Now, if we want to continue to find the new yield strength of the material, then we have to convert areas to length. And length is, we know that the strain is ln of L over L0, and this is ln of A0 over A. So knowing that, we are able to use the the information that we got on the change of area and compute the strain. The strain is large, is 16%, and therefore we know that this is in the plastic regime. It is above 0.2%. 0.2% is the limit that differentiates elastic. It will be less than 0.2%, and plastic will be greater than 0.2%. So here I have 16.25%, which means that in plastic regime. And it's large deformation, so we could use the Ramberg-Osgood formula directly, ignoring any differences between true and engineering stress, and therefore we use it here, that the new yield strength of the material is sigma 0 times epsilon I to the power m, and plugging in numbers, we obtain a new value of the yield strength of the material as 57.1 KSI. Let's compare that here to the original yield strength of the material was 32 KSI. Therefore, the material has improved in terms of the strength, and the 32 KSI became 57.1%. The ultimate strength, the new ultimate strength of the material is obtained from force equivalency at the ultimate, which means that the ultimate strength times corresponding area is conserved. And that gives me the ultimate strength in the new work hardened material as the ultimate in the original state of the material divided by 1 minus W, and that makes a small change from 49 to 58 KSI. Now, this next example that I'm going to discuss is on hardness. And hardness of the material is a measure of the surface property. It's very expensive to do a lot of tensile testing, and in many manufacturing outfits, it will be very costly to do extensive testing. Therefore, the surface can tell us a little bit more about the strength of the material. Two different measures of hardness have been described in the literature. Hardness is to get an indenter, looks like the pen with a tip, and the tip could be shaped very similar to this pen. And then you have the surface, and then you push hard on that surface, and you measure the force and the displacement of the tip of the pen as it goes through my skin here. So this is the hardness of my skin. This measure is called Rockwell hardness, and it has 3 different scales, A and B and C, depending on the shape of that tip here, the conical shape. So it could be small, it could be large, and it's used extensively to test how hard steels are in practice. Another way is to have this tip, instead of having it pointed, is to have it with a hemisphere at the end. So you have a hemispherical tip, and you push hard on the material, and you see how far the hemisphere is going to penetrate into the surface, and the relationship between the load, and then the hemisphere is going to have a contact area. So the contact area can be measured. So if you measure the load and then you divide it by the contact area of this hemisphere, I'm going to show it here. So I have the hemisphere here, and then the surface is like, let's say here. So this is the surface. This contact area here that I'm thickening, it has an area A, and then if I have a load P, so the ratio of P over A is the Brinell hardness number. So we have two different scales. One is Rockwell and the other one is Brinell, but both of them are in units of stress because they're load divided by the penetration area. Now, the advantage of this is that if I can find a correlation between the Rockwell or the Brinell hardness number and the strength of the material, I do not need to do extensive mechanical testing. I can just push on the material, and from pushing the material, I get a number. I have actually a dial, boom, I can get a Rockwell number or a Brinell number. And then if I have a conversion, if I have a correlation, that can gives me an indication of the strength. In fact, this idea is so simple, but many industries have been based on this idea. Startups and bigger companies that people develop testing machines, devices that can just go and test and the advantage is that you can go on piping and then you can test it in situ and give quick information. Very, very useful. So it turns out to be that for steels, which are ductile, the ultimate strength of the steel is about half of the Brinell hardness number if you measure it in KSI. That's amazing, right? So if you just get a Brinell number of 100, then the ultimate strength of the steel will be 200 KSI. Fantastic. Another, for cast iron, the ultimate strength is given as 0.23 of the Brinell hardness number minus 12.5 KSI. In other words, the ultimate strength is 1/4 of Brinell for the cast iron, and then also less than that, minus 12.5 KSI. So let's take an example on this application. We have a foundry, and the foundry is producing parts, but then there's going to be inspectors, and the inspectors are going to come and they want to know that the ultimate strength of the cast iron is within a certain specified range, otherwise they would not accept it. So they specified, we want to know that it exceeds ASTM's, the American Society of Testing Materials Standard number 20 specification, which has a table here. And that specification is that the ultimate strength of the cast iron should exceed 20 KSI. So how do we know from the foundry? So all what you can do is we want to determine what is the range of the Brinell hardness number that we can have on our dial, and then we can go and test different samples. From the previous relationship, if I want to have H Brinell, then I can take the S ultimate and I take the 12.5 to the other side and then divide it by 0.23, and that should give me the value of the Brinell number that is acceptable. And in this case, when we do the calculations, it's 141. So any Brinell number above 141 will guarantee that the ultimate strength of the cast iron is 20 KSI. And in this case, it is acceptable to be in the range 145 to 165, and that would be grade ASTM grade 20, meaning that the ultimate strength is 20 KSI. So with that, we will stop here, and we'll see you on my next video. Thanks for watching.